Or 99% of people believe insects are small. That's mostly true today. But millions of years ago, insects achieved staggering, almost unbelievable sizes. Imagine a dragonfly with a wingspan longer than your arm today. This wasn't mutation, it was dictated by the very air they breathe. We must understand the fundamental difference: atmospheric oxygen concentration. During the Carboniferous period, oxygen levels were significantly higher, nearing 35%. Today, oxygen sits near 21%, a crucial difference for arthropods. And now that we understand the air, let's explore how insects breathe. Insects do not use lungs or blood to carry oxygen effectively. They rely on a passive system of tubes called tracheae and tracheoles. Oxygen must diffuse passively across these tubes directly to the cells. Diffusion is highly efficient, but only across very short distances, limiting body size. If an insect doubles its width, the distance oxygen must travel quadruples. This geometric reality places a hard physical cap on arthropod dimensions. But what if the air itself provides more gas molecules to work with? When oxygen is plentiful, diffusion becomes less of a limiting factor for size. The higher partial pressure of oxygen forces diffusion deeper and faster into the body. This allowed ancient relatives of millipedes to reach lengths exceeding 2 meters. Their tracheal systems, while passive, were simply better supplied by the atmosphere. The oxygen abundance was driven by colossal swamp forests of lycopsids. These plants produced vast amounts of organic matter, which trapped immense amounts of carbon. This effectively removed carbon dioxide from the atmosphere, boosting residual oxygen. The largest flying insect ever, the griffin flea, also benefited from this high oxygen environment. While size is limited by diffusion, flight demands even greater respiratory efficiency. Some ancient insects may have utilized more active ventilation, using body movements. A higher oxygen allowed for a higher metabolic rate to support that immense musculature. But this golden age for giants could not last forever. As the Paleozoic ended, continental drift and volcanic activity changed the air composition. The massive carbon sequestration forests eventually died off, returning carbon to the cycle. But as oxygen dropped back toward 20%, the size limits reappeared instantly. The massive arthropods simply could not sustain their bulk with less available oxygen. This environmental shift is why modern insects remain remarkably small in comparison. They evolved efficiency and speed, prioritizing rapid movement over sheer mass. It's a classic biological scaling problem, solved differently by different creatures. Vertebrates, like fish and mammals, bypass this issue using circulatory systems. Blood, containing specialized oxygen-carrying pigments, actively transports gas throughout the body. This active transport mechanism allows for much larger body sizes, even in low oxygen. If oxygen levels rise dramatically again, What might we see emerge from the shadows? Well, hypothetically, a 10% rise in oxygen could allow insects to grow substantially larger. But modern terrestrial life has evolved under different pressures and constraints. In exoskeletons, muscle structure, and predator-prey dynamics also play vital roles today. But the key takeaway remains rooted in gas exchange efficiency across geological time. Giant insects are not anomalies, they are direct physical evidence of ancient air density. But this principle extends beyond terrestrial insects to all life dependent on diffusion. The physical constraints of diffusion set an invisible ceiling for passive oxygen uptake. The massive flora that produced that oxygen also provided the food source. On a high-oxygen world supported larger primary producers, fueling larger consumers. Energy transfer across these massive bodies required maximum respiratory support. Though when the forests vanished, the oxygen engine for giantism shut down permanently. The shift was relatively swift on a geological timescale, forcing immediate adaptation. The largest individuals would have suffered from severe hypoxia almost immediately. A natural selection favored smaller body plans that could survive on reduced oxygen. But we, too, are subtly constrained by our own atmospheric composition. If Earth's oxygen dropped too low, our own circulation would fail rapidly. Biological limits are absolute. They are dictated by physics and chemistry. The giant Griffenfly soared because the air itself was thick with its required fuel. Understanding these giants means understanding the power of planetary chemistry. Atmosphere is not just empty spacing, it is the fundamental physical constraint on size. Today's world supports mammals, birds, and smaller arthropods perfectly adapted to 21%. And the giants are gone, but their massive legacy is written in the air we breathe.